All right, here we go. This is question number 2 from the 2019 Calculus BC exam. That means that this is a calculator active question, so go get your calculator. And as you can probably see right from the very beginning, this question is going to involve polar curves. And I know that this is something that we don't get a lot of practice in the pre-calculus course, and even in the Calculus BC course, we have to go really quickly. So pay attention, get as much out of this as you can, and we'll take it from there. Okay. All right. It says, let S be the region bounded by the graph of the polar curve r of theta equals 3 times the square root of theta times sine of theta squared. Now, I do not know anybody that would just know what that graph looks like. Not expecting that you know that. The College Board gives you the graph. This is a calculator active question, so we're going to take advantage of all those things. For the interval 0 less than or equal to theta less than or equal to the square root of pi, as shown in the figure above. Okay, so we've got all of that information, and they want us to find the area of S. So one of the things that you need to remember is that when you're dealing with polar curves, the way we find the area is it's 1/2 the integral of your radius squared with respect to theta from your starting out angle, normally we call that alpha, to the ending angle, normally we call that beta. And I think this one's going to be a pretty standard problem. They tell us that r is this 3 square root of theta sine theta squared, and that our angle ranges from 0 to the square root of pi. So my setup is going to be 1/2 integral from 0 to the square root of pi. R is 3 square roots of theta, sine of theta squared, all of that is squared, and we're integrating with respect to theta. Okay, sorry, trying to get some of these things off the screen. All right, so we are absolutely not going to try integrating this by hand. That would be crazy. Instead, we're going to switch over to the calculator, and we're graphing a polar curve. So we're going to have to change things up a little bit. We're going to go to menu. We're going to go to option 3, graph entry edit, and we are going to select option 5, which is polar. And so now I see rather than r of theta, it says r1, just like we would expect with f of x. It always says f1 of x. And now we're going to type this in. So 3 times, you now need the square root of the theta, I believe is in the pi button. There it is. Okay. And then 3 square root of theta times, let me actually put in the multiplication sign, sine, so sine of theta, and that has to be squared. Okay, my angle is supposed to go from 0 to the square root of pi, and even here your calculator is going to be super helpful, so we're going to do control square root and pi. You're going to hit enter, and look at that. That is exactly the curve we were expecting to see. This matches what the College Board gave us. Now, the reason that we're going to put the graph here is so that I can then switch over to the calculate screen, and we're going to put in that integral expression. So it was 1/2 times menu calculus. I'm going to do a numerical integral. Our lower limit is 0. The upper limit is square root of pi. And I don't have to type in the 3 square root of theta sine theta squared. I already have that. What I do have to keep in mind, though, is the name for that function. It's r1 of theta, so I'm going to do open parentheses. We're going to do r1. Shows up in bold. That means that the calculator recognizes, oh, this is a function already. And you can do the integration with respect to theta if you would like. It's r1 squared. Integrating with respect to theta. There we go. You could have also done this with respect to x if you would like to. As long as you're consistent with the variables on this screen, it won't matter. And your final answer is 3.534. All right, let's go back to the paper. So that means that my area is approximately 3.534. Now, how did the College Board award points for this? 1 point for your integral. That's all of that work right there. And then 1 point for the answer. Grand total of 2 points. These are 2 points I would expect everyone is going to be able to earn if you have any working knowledge of polar curves. You're going to have memorized this area formula, and now you're going to apply it. Writing down the formula is something I would encourage you to do. It's not going to earn you points, but it is going to be a good way to trigger your memory, and I would do this every single time I'm working on an area problem. All right, let's keep going. Part B says, what is the average distance from the origin to a point on the polar curve? Sorry, we're getting a little blurry here. Not sure what's going on. The document camera's having some struggles this morning. What is the average distance from the origin to a point on the polar curve for that interval 0 to the square root of pi? Well, let's get something straight here. In polar, the way that we're measuring distance, you're measuring distance from the origin out to the curve. And you might think, oh, we need a distance formula. If we were working in terms of x's and y's, if we were in a rectangular coordinate system, you'd be correct. But in the polar coordinate system, you have an angle, and for that angle, you have a radius. The radius is going to change as your angle changes, right? I always imagine like my angle is increasing, increasing, increasing. The radius changes, but I'm always going from the center to the outer curve. So the distance is actually your radius as long as your radius is positive. Well, how do we find an average distance? So part B, the question was asking about an average distance. Well, you know, in calculus, when we do an average, it's always 1 over b minus a, the integral from a to b of f of x dx. That would be the average value of this function from x equals a to x equals b. The average distance for this problem, well, we're integrating from 0 to the square root of pi. We're integrating r of theta with respect to theta. And since we're integrating from 0 to the square root of pi, this will be 1 over the square root of pi minus 0. That is your setup. We're now going to go to the calculator again. We're going to type everything in. So what do we need? We need 1 divided by your square root of pi. Just want to be really careful when I type this in. Okay, we're going to multiply this by the integral, numerical integral, from 0 to the square root of pi of r1 of theta. Come on, theta. There we go. And we're integrating with respect to theta. Keep in mind, I'm going to do all of this work on my calculator. I'm not trying to do any of this by hand. And so my answer here is 1.580. Let's go back, and the answer is approximately 1.580. College Board awarded 1 point for having this expression right here. They awarded another point for your numerical answer. So a grand total of 2 points. Not too bad. These are still points I would expect lots of students to be earning. Let's keep going. Oops. Sorry about that. All right, part C. There is a line through the origin with positive slope m that divides the region S into 2 regions with equal areas. Okay, we got a lot going on. We're going to come back and read that in a bit. Write but do not solve an equation involving one or more integrals whose solution gives the value of m. All right, that definitely bears repeating. Let's try that again. There is a line through the origin with positive slope m that divides the region S into two regions with equal area. Okay, what does that mean? I've got region S. Region S is this region. Oops, that went too far. The region starting at 0 all the way out to when the radius gets to the square root of pi. And their claim is that there is some line, I don't know where that line is, but the slope of this line is m. What makes that line so special is that it's going to divide region S into two regions that have the same area. Now, this is just a representative line. Those areas, the area below the line and above the line, they're not going to be equal. But think about what you would need to do here. You already know what the total area is for S. We already figured that out. We need to come up with an integral expression in terms of this line, the slope of the line m, that I can use to figure out where exactly is this line. The thing that we want to keep in mind is that when we look at doing area and polar, you need a starting angle and you need an ending angle. So knowing that your slope is m is great, but unless you actually know what the angle is that gives you the just right slope, you're kind of stuck. So let's get clever with this. What I know is that the total area, the area of S, is, what did we come up with in part A? We said the area of S is 3.534. My goal is to have an area of 1/2 of that. So 1/2 of the 3.534. And I need to figure out the value of m, or an equation that involves m. What I know is that the slope of the line is m. And how do we find slope? Your slope is always the y value over your x value. What we need to keep in mind, though, is that in this sort of a problem, when we say the slope, we've got to connect it back to the angle. So if I think about this for a second, here's your x, here's your y. How would I connect the slope to this angle? Well, I know that the tangent of the angle is the opposite over the adjacent, so tangent of theta is y over x. So when we talk about the slope, that's also talking about the tangent of the angle. What I need is that angle such that the tangent of the angle is equal to m. So think about that for a second. M is tangent of theta. That must mean that the angle I'm looking for is the arctan of m. Now, before you freak out too much, you don't need to know what the specific value of m is. What we need is an expression in terms of m. So if I integrate, if I find the area from 0 to this angle here, the arctan of m of my function r of theta, this would be the area from 0 up to that line. It's supposed to be equal to 1/2 of the total area of S, which is 3.534. You could write it this way and get the points. You could also imagine writing it this way, that if I find 1/2 the integral from 0 to arctan of m, r of theta squared d theta, that's going to equal the area if I integrate from arctan of m to the square root of pi of r of theta squared d theta. That's great. You could also have just written it this way and said this is 1/2 the integral from 0 to arctan of m, r of theta squared d theta, is equal to 1/2 of the total area of S. Lots of options of how you choose to write this. Any of these three will do it. I'm sure there's other ways you could do this as well. So let's look at how they awarded the points. So they awarded 1 point for using the arctan relationship to express the desired angle in terms of M. Then they said 1 point for equates the polar areas and 1 point for the equation. So I'm reading this as you used one of these relationships here and you used it correctly. So it seems like they're saying if you equate two different polar areas, we're going to give you a point, even if maybe you've made a mistake here, if you've made a mistake over here. But if you're able to get any of those equations correct, that's going to get you 2 points for a grand total on this one of 3 points. Not bad. All right, we've got one last part to go. Let's see what we can do with this. This one is definitely going to push you to think a little bit differently. I've never seen them ask a question quite like this. And honestly, the first time I saw this, I was a little stumped myself, and I kind of took a leap of faith, and I was right. But let's see. For k greater than 0, let A of k be the area of the portion of region S that is also inside the circle r equals k cosine of theta. Find the limit as k approaches infinity of A of k. All right. For k greater than 0, let A of k be the area of the portion of region S that is also inside the circle r equals k cosine of theta. All right, I want to find the limit as k approaches infinity of A of k. Before we get into this too far with the actual calculus, let's go over to the graph. And I want to show you something that I think might help out. I'm also going to zoom in a little bit so that you can see. Let's zoom in. Okay, see the graph a little bit more completely. And I can't graph r equals k cosine theta, although actually maybe I can. Let's try this. I'm going to go to tab. R2 we're going to say is k times cosine of theta. Come on, k cosine theta. All right, now, yeah. What I'm going to do is I'm going to create a slider for k. So r equals k cosine theta. Right now, it looks like k is equal to 1. Why am I not seeing the graph here? Let's see. Let's go back. I should not experiment with things like this while I'm doing the video. R equals k times cosine of theta. Theta is going to vary from 0 to 2 pi. Right now it looks like k is equal to 1, and I want to change that value of k, but I'm not seeing the graph. Okay, bummer. Sliders didn't work. Take 2. Okay, so what I'm going to do is, rather than doing it with sliders, let's try different values of k, like r equals 2 times cosine theta. Create a slider? No. Interesting. Okay. 2 times cosine of theta. All right, I think I know what's going on here. All right, we're going to go to trig. We're going to select cosine. Come on now. Cosine. We're going to select my angle of theta. And now we're going to graph. Okay, so here's the graph of r equals 2 cosine theta. What we're looking for is the area that is between the red curve and the blue curve. That's like all of this part over here. Now, there's ways that we can do this. We've talked about this with polar coordinates. But here's what's happening. They're not interested in r equals 2 times cosine of theta. They want us to change the value of k. So imagine r equals 5 cosine theta. Here's a new circle. The red curve is obviously bigger than it was before. The center is out here. We're passing through the origin. I want the part that is below the red curve and above the blue curve. If I let that value of k get larger and larger and larger, so let's say r equals 20 times the cosine of theta, what happens is the circle just continues to get a larger radius. And what happens is you're still looking for the area between the red and the blue. Well, what if I let the value of k get really big? Not like 20, but how about 200? And let's hit graph. You now have a circle that is really, really, really large. So large it doesn't even look like a circle from our perspective. And I could let that value of k get even larger. What's going to happen is that in the limit, that red curve is actually going to become a vertical line. And the area that we're going to be looking for is the area between that vertical line in the limit case and the blue curve. That is the area of S if I only let the angle goes from 0 to pi over 2. So let's go back over to the paper and write this down and think through this. We've already looked at A of k. A of k is the area between the red curve and the blue curve. In the limit that k approaches infinity, what we get is the area from 0 not to square root of pi, but 0 to pi over 2, 90 degrees, that vertical line of r of theta squared d theta. That's what the limiting case is going to be. So if I go back over to my computer, and we're going to do one last calculation, numerical integral. We're integrating from 0 to pi over 2 of r1 of theta. Come on now. R1 of theta squared. Integrate that with respect to theta. And the final answer is incorrect. Oh, I know what happened. You see it? I forgot to multiply this expression by 1/2. So let me go back over here and put in the 1/2 times that area. And that's going to give me an area of 3.324. So this final answer is 3.324. The College Board offered 1 point for the limits of integration. So basically you're recognizing that you're supposed to be integrating from 0 to pi over 2. They awarded 1 point. And then they said answer with integral. So they needed to see this setup here, not just the 3.324 floating in outer space. So that would bring you the total of the 2 points for part D. Not bad. I know that video was a little bit long. I think what happened earlier with the slider is that when I typed in cosine of theta, it didn't recognize cosine as an actual function. And anyway, sorry about that. But you can go back, you can try the sliders on your own, and I think that'll work out nicely. Good luck.